Okay, we are live now. So I welcome all of you for another edition of the Wednesday Colloquium. And I have deep pleasure of introducing a very good friend, Professor Dinesh Kabra, from right like one and a half hour distance from us at IIT Bombay. He is sitting right in his office and going to give us a glimpse of how organic photovoltaics have made it to the contemporary technologies now that they can match with the best solar performing solar cells in the market. So before Dinesh goes and delves into the details of the science that he wonderfully does um, in India, I think one of the leaders in photovoltaic community in the world, and is brought lots of very interesting things developed in India. He has done a lot of development in India, so we will hear that. But I just wanted to sort of briefly give a overview of what the Wednesday Colloquium really means to all of us, because Dinesh is sort of new to this. So it's for Dinesh and for all those listening for the first time. So the Wednesday Colloquium actually has its bearings from Homi Bhabha, because he was the founding director of TIFR, and he instituted this idea that all scientists, irrespective of being a physicist, chemist, or biologist, should get together once a week. And it will be a forum where people from different areas of expertise can come and give talks which would appeal to a broad class of scientists, so that everybody gets involved and sort of sees where contemporary science is going. So this tradition has been built very strongly in the institute, and I'm lucky to be serving as a colloquium coordinator, and many of the audience have contributed to actually keep this tradition going for all these years. So with that short summary, I would like to proceed and formally introduce Professor Dinesh Kabra. So Dinesh actually did his PhD from JNCASR, Bangalore, and he worked with Professor K.S. Narayan. I think you were Narayan's first student, or close?
No, I think I was fourth
Fourth,
or fifth.
fifth student.
Yeah.
Okay, and and by training in Professor K.S. Narayan's group, Dinesh actually got into making devices, and he actually developed himself as a device physicist, and doing a lot of transport measurements as well as other sort of aspects of devices. Um, uh, from that point on, after finishing his PhD, he actually moved to his position in Cambridge, University of Cambridge, as a postdoctoral research fellow, where he worked in the group of Professor Richard Friend, who actually is the pioneering person who sort of first demonstrated a working organic photovoltaic device. In his group, he actually looked at coherent optical sources using micromolecular ordered structures, and as well as sort of put together both optical measurements as well as looking at the device physics of organic photovoltaics. Um, in fact, I would say it was a very rich experience that Dinesh had there. And he made his way into also doing a lot of, working with a lot of conjugated polymers and looking at photophysics of conjugated polymers. He actually won a Herschel Smith Research Fellowship Award, which allowed him to work for 3 more years in University of Cambridge. And then he came back to India, to his own country, where for last 8 years or 9 years, he has been sort of working and developing technologies related to organic photovoltaics and light emitting diodes. Both from the aspect of being frontier in the world. I think I have followed his work quite a bit. In fact, when I need numbers of efficiency, and I need to know which material is performing so well in photovoltaic community, I think I just call him up, and he he already either is working on it or he already has a published result. So Dinesh, I really look up to your work, and it's a pleasure to listen to you about how contemporary organic photovoltaic technologies are changing the solar cell market. So thank you for giving this talk and this opportunity that you're interacting with us. So Dinesh, it's all up to you.
Thank you very much, Professor Jyotishman, and of course, old friend. And it's a great opportunity for me, and I'm really honored to be part of TFR Wednesday colloquia, where I will be having the variety of audience. And I thank you all of you for getting the time and coming up for this Wednesday talk. I'll be sharing my slides, and we'll go into the talk which we are here for. Is the slide visible? Hello?
Yes, perfect, Dinesh. Sorry, I was muted. Yeah.
Perfect.
Yeah.
Okay. So as I already said that the stock will be as prepared based on the excitonic materials, which are hydrocarbons. And we are going to say that how does a journey of this hydrocarbons based semiconductor has make their way from efficiency, which was 1% or even less than 1% to close to 20% by today. And it question how is put up, because that's what the question even I was having when I was seeing this continuous growth in the power conversion efficiency of this new kind of emerging photonic materials, which always had the questions whether that will ever reach to this kind of number. But what has made us to see all this thing happening will be covered up in this talk. But first, before going to that one, I should basically acknowledge the people who are responsible or
Dinesh,
who are really doing the work because of which I can make this presentation.
Dinesh,
Yes.
Sorry, we can't see you, Dinesh. Your video somehow got off.
Oops. Just a moment.
एक बार just Zoom में जाके वीडियो को ऑन कर लीजिए. आपका वीडियो बंद हो गया.
Should not be. My video is on. Top
अभी
video.
ऑन है. नहीं, हाँ ऑन हुआ. अभी ऑन हुआ. अब फिर से शेयर कीजिए स्लाइड्स.
So it shares the screen, and then I
ऑफ हो गया. अरे ये क्या हो रहा है? आप जैसे ही शेयर कर रहे हैं ऑफ हो जा रहा है.
So I stop. So right now you are seeing the screen.
हाँ, राइट नाउ ना अभी दिखा रहे हैं यू आर शेयरिंग स्क्रीन. ऐसा एक कोई आपका टैबलेट या किसी से आ रहा है?
Yes, I am doing from the iPad.
अच्छा, iPad. Okay.
So and then I go to the screen which I need to share, and that's the screen here.
Okay, then the video gets off. Anyway, you continue. We will fix that later. ठीक है? जब question answers में, then we can take the video on.
Okay, fine. Or should I switch to laptop?
नहीं, कोई issue नहीं है. कोई issue नहीं है.
Okay, fine.
Continue.
Okay, fine. So the people who are really making me stand here to give this talk are listed here, and these are the people who are coming from as a postdoc, PhD students, and at the same time collaborations. Professor K.L. Narasimhan, Achinta Venugopal. These are my collaborators who have come from the institute where I'm giving this colloquium talk. And there are many others within the country and outside country. Of course, I should basically acknowledge the generous funding coming from the public funds, Department of Science and Technology, Ministry of New Renewable Energies, and some of the UK government funding. And at the same time as the work is being applied, so there are the industries also involved, and where I am getting a good support, in-kind support from Applied Materials, US companies, Cambridge Display Technology, UK, Corning Glass, USA. So some of those kind of companies are basically giving in-kind support to all these research activities. So they are here. People who are who have contributed in some way in coming up slides are with faces here. Amrita and Nakul are postdoc in LMU and link shopping by now. Urvashi is current grad students. Gangadhar is current grad students. Dhanashri is our ex postdoc, and she is left. And Naresh is again the old grad students. He is right now postdoc in IMAC, and they are the other faculty colleagues from the various institutions. Anil is in-house, who are really making us to understand the things which is difficult to understand by just ourselves. So these are the people who are a part of this whole exercise. Now the question is, like when I was talking about the solar cells, the question comes, why solar cells? Why? Because solar cell is part of the renewable energies. And so why renewable energies? So the question's answer is that you look around, you see the changes in the air quality. Environment is changing continuously. We are seeing the air quality is continuously degrading. We have lots of such kind of news coming from Delhi, smoke, and the other part of the world. Water quality, and lots of hazardous materials coming up because of the uses of the various kind of new technology products, and we are collecting lots of waste. And we do not understand that with the advancement in the medical field, world population is going to continuously rise, and particularly in our continent, the way the kind of lifestyle is changing, and the world population is going to mark towards 8 billions in coming few decades. Energy demand is going to go high. From where this energy has to come? And those questions needs to be answered by this generation, because our next generation will need those energies. And the answer is, we have to go towards renewables, because by definition, renewable never ends. So we have to look for the solutions in the form of renewable energies. We can't rely on our already deposition of the fossil fuels, etc. When I'm talking about this thing, at the same time, it provides job security. It provides the economy to boost, because the renewable energies are in general done by the local. It's being installed at the local sources. You don't really want to carry those energy to the long distances. So that basically helps to the local economy, and also it opens up new opportunity to be part of, and also allow us to become the part of the technology leaders. And one of the example is what I'm talking about, organic solar cell. We'll see in coming few slides. Energy security is another big buzzword, which is really all around the globe. People have realized this thing. Dependence on the imported oil and natural gases with increased demand is alarming. We have to find our own Atmanirbhar Bharat. Self-reliance is needed. So we have to produce the energy using our own systems, our own materials, instead of really being dependent on others. So renewables are needed. In the renewables, the way the energies are being used consumption wise all around the world. So we do see that the climate change is happening, global warming is happening, and that is happening due to the carbon dioxide emission. And the way the energy is being produced, and those energies are basically producing the CO2 emission, that chart is basically shown here. So it's still a major portion of the energy which for the electricity is being generated using the coal and natural gases. And we have renewables coming up here, which are still very, very less as compared to what we should be really targeting for in coming few decades. Otherwise, we are going to face the issues in terms of climate change. Glaciers will be melting. Overall, the global warming will be happening. So those all consequences will be there on this planet. And what can happen is another extinction. Earlier, the dinosaur went. Sometime with the temperature rise, other organic body might evaporate from here, and that is human. So we have the solution in the form of many aspects, but in the terms of India, where we have fantastic solar flux. One of the solution is, let's go towards the solar cells. And one of the example in the solar cell technology I'm basically citing is silicon based solar cells, and there are the reasons for that, which we'll be discussing in coming slide. But good thing what has happened in the silicon solar cells is over the time since 1975 onwards, when the commercial silicon solar cells started being manufactured. So the energy joule per dollar for the uh, energy has gone really, really high for the silicon solar cell, which is black data point, and the oil pricing, which has all the kind of jigs and jags, which is blue graph over here in the inset. So we have got continuous decrease in the silicon solar cell, which mirror image is there in the black graph. So because the cost of the silicon solar cell fell down, and it was and efficiency has improved over the time, so we could get more energy per dollar using the silicon solar cell as compared to our, as we were relying on the oils to produce that amount of energy. So there's a clear cut and why the cost came down, that I'll show you again. But it's a clear cut telling that yes, it's good to go towards the some of that kind of solutions to make things better and make things more sustainable over the time. Particularly in the solar cells, these are the gigawatts. Let me tell you, the kind of typical PV panels for a small household, 4 people, requirement is hardly like between 5 to 10 kilowatts. So these gigawatts can take care for the like mid-sized cities. If you have gigawatt installations, generally you will find lots of government projects with tens of megawatts and all. So the government National Solar Mission of India has put up a mission to install 300 gigawatt of power generation using renewable energies. And in this 300 gigawatt, which includes everything, wind energy, bioenergy, hydro, on the solar cell, particularly considering the India where the solar flux are pretty good, 100 gigawatt is just for the solar energy. And there's continuous growth in the PV installations. And this is for the world chart, which has moved pretty drastically. And it's on the y-axis on the log scale and x-axis on the linear scale. So you can see there's exponential growth in the PV power, solar cell generation power over the years. And that suggests that once the so much of volume of the solar cell is being produced, then the Swenson's law suggests that the green line, which is a simulation, a model, that a 20% decrease in the price for every doubling of the cumulative shipping of the photovoltaics. So as the more and more solar cells are being manufactured and those are being installed, the cost of the solar cell is continuously decreasing. And actual decrease in the solar cell is much steeper than what that model had predicted in the last 5-10 years. If you look at the since 2010, the blue graph, which is experimental real life data, is for not following the experimental simulation model. And the data which I have is like in sometime 1976, the dollar per watt using a silicon solar cell was $76, which corresponds to something like 5,500 rupees per watt, has gone down in 2015 to $0.3 per watt. $0.3 corresponds to almost like 25 rupees per watt. This is the kind of power which right now we are paying using the silicon solar cells, which are coming commercially available. So 25 rupees per watt. And how does that basically goes into the real calculations that we will see. So the overall idea is that there's a tremendous changes. The PV power is becoming cheaper, and it's gone down to 25 rupees per watt. So that's good news. And in Indian perspective, which is
Dinesh, I
yes,
just like to sort of add here. This
yes,
is a very interesting story that relates to history of TIFR. Homi Baba, of course, was a proponent of nuclear energy, and
yeah,
a lot of money he brought in making of course, sort of the idea of government funding nuclear power plants. And at that time, when 40s,
yes,
50s, when India was just getting independent and becoming a nation, But at the same time, there was a mathematician and a scientist at TIFR, D.D. Kosambi, Professor D.D. Kosambi.
Okay.
He actually was a proponent of solar power.
Okay.
And he predicted that solar power in India would change the landscape for India. And
Oh,
of course, Kosambi and Bhabha did not get along on a personal level because there were some political differences and as well as some ideological differences. But
yeah.
it's kind of interesting that Kosambi's vision is now what the government is going to follow in the next, 10, 15 years.
I think it's worldwide. Yeah, wherever the right there, wherever we have the good solar flux, uh, Australia, India, these are the country, Mexico and Spain. So these are the countries which have really religiously now using PV as a best solutions. Not only just in the solar cell, but in the solar thermal, which I'm not going to cover. But there are the really good opportunities to be availed. And MNRE, this is our India's perspective where we are seeing how is India doing. This is the numbers in megawatts, and we see that the renewable energy has taken like more than 20% the overall power generation, which is very good news. And with the current vision of the government, we are going to go further higher. So, and these are the states where if you look at the Rajasthan, Telangana, Karnataka, which is peaking as well. So these are the states where the lots of PV installation is already done by March 2019. And the mission is 300 gigawatt, where we have the solar alone 100 gigawatt. However, when I make all these things and these all positive things are happening, I have some worry because the silicon solar cell power is coming 25 rupees per watt, which is generally for the polycrystalline. Now the technology has moved to monocrystalline, which is almost like 40 rupees per watt. So there's not much difference. However, there's a whole silicon solar cell modules require lots of things. In that, lots of things, encapsulant, junction box, and the glass. These are the only three things which is coming from India. Rest, everything. We don't have silicon refinery. We have aluminum ore here, but still we don't use aluminum framings, which is required for silicon modules coming from India. Those are coming from outside. Silver paste. So the most of the ingredients are imported. And so if I talk about this 100 gigawatt just for the not balance of the system, just for the silicon modules, we are going to have a Indian currency in the US dollar, something close to like 30 to 40 billion dollars will go out of the country. This is for the installation and all about research. I'm not counting, which people are doing on the silicon wave using silicon wafers. So the problem is here. We are planning to open something big installations, but the very much raw material is not available to us. We don't have this technology where a sand can be converted into an electronic wafer. And the silicon is being used in 95% of all installed PV modules today. I'm not even counting for the microelectronics here, which is again, so sometimes there are the few people who make the presentations, they suggest that beyond silicons, because the amount of money which is going to be spent on importing the silicon wafer might cross the crude oil if I'll be talking about PV plus microelectronic industries. So
Who
we
is
have to
who is the leader in silicon wafer? Companies in China or US?
China nowadays, yes.
China. Okay.
Yeah. So earlier it was US, but now the China has beaten up them. So they are the one who are really the leaders for each and everything. The aluminum frames are coming from them. Silver paste is coming from them. So if we, and in coming years, the wars are not going to be fought with the weapons. Those are going to be fought only with the sanctions. Okay, we won't give you this. Now go and see how do you survive. So that's what world energy security is buzzing big. So the solution is there if we want to exploit, and that is before PV, the solar energy was being converted into useful energy, and those things were done very nicely by the tree and plants. tree and plants can do this thing with very decent efficiency with 6%. We have huge barren lands, and where if somebody don't want to use real technology, if they just grow the trees by doing some hard work, we will still have a better world to live in. But we are talking about the something called artificial photosynthesis, which is there in this paper. Are organic semiconductors viable for robust, high efficiency artificial photosynthesis? So plants were converting solar energy into the chemical energy, but we need something more better form of the energy. We want to use that solar energy, which is coming free of cost to us, and we want to convert them directly into the electrical energy, a different kind of transducer. So we come up with the answer is organic solar cells. And this is one of the example of the artificial photosynthesis. There's a tree where the leaves are made up of organic solar cell panels, as the flexible organic solar cells, which can basically harvest the incoming light and energize the objects which are around, or you can use that power overall. So that is the answer. Yes, we have solutions which can go beyond silicon, and we have lots of petrochemical industries in our country who can provide those monomers, and which can be cooked well, and chemistry research is doing pretty well in our country. There's no doubt about that one. So there are the solutions. It's just that whether we want to use them or not. And these organic semiconductors are indeed very different from our classical silicon based inorganic materials, which are covalently bonded. But here we have these molecules, and those molecules are just sitting together using the van der Waals bonded using van der Waals forces, and they have a very different transport physics, photophysics, which we'll be discussing. And to be very frank, when I started working with organic semiconductors, which were something of that sort of this vials in which I was getting the solutions of the MEH, PV, or some kind of organic semiconductor solutions, which looks like dyes. It's some of the dyes which we have been seeing in our life every day. So these are some of those dyes, but with some special properties in terms of having the conjugated or alternate single bond, double bond, which allows them to not only show different colors, but also do the charge conduction. But the charge conduction used to be in the range of 10 power minus 5 to 10 power minus 7 centimeters square per volt per second. With this kind of mobility numbers, there were always questions that is it going to survive against these shiny wafers, which has got mobility in the range of 1,000. And those wafers are based devices are highly reproducible, they are very stable, and efficiencies were like with the silicon is always 20 plus from last few decades. And these organic semiconductors, which in early 2000 were lots of questions mark. Okay, what are you working on? Are they going to make any impact ever? And then we waited. People continue to work with them, and today what we have in our hand is lots of real life product. Many of us are holding OLED displays. Display industry has done pretty well using organic semiconductors, and those are gone something like a few $billion industries. And this is the organic solar cells based industries on the right side of this slide, which believes that organic solar cell is going to make some impact in coming decade. And these are the companies which I could basically pull out by my own research. There might be more than this one. And this is the basically the chart which suggests that how the journey started. I'm showing some early results. 1883, first solar cell was discovered by the Charles Fitts, and then Bell Lab made first solar cell in 1954. 70 years passed, but still we are skeptical whether I should use silicon solar cell panel on top of my roof or not, because the grid parity, still I can get the cheaper electricity directly from the government. So why should I basically put up an extra load on my roof, which will take away my roof space, and still it's going to be expensive, because by the time the financial payback, if I had to invest lakhs of rupees to install those panels, people start counting for the people started looking to the economics. So those questions have put the all the PV industry on the halt for the local house level domestic uses. It's the happening on most of the like government bits are happening, but like domestic uses, the building integrated photovoltaics or domestic use is still not there because the technology seems to be still expensive. Though I said now we have gone from $76 to $0.3 per watt. And meanwhile, in late 80s and 90s, Richard Friend and Alan J. Hager almost together shown pretty decent solar cell efficiency, close to 1% using polymer and polymer fluorines. And polymer did not really kicked in so well. Polymer fluorine took the pace further. P3ST PCBM, which is one of the fluorine derivative. What is fluorine? Fluorine is basically a carbon-based ball. There are the 60-70 carbon atoms sitting together to form a ball, and those are fluorine, which has got again lots of nanocarbons-based materials, which has got few Nobel prizes in various different kind of geometries when it was in the shape of football, when it became a sheet. So those all things have really nanocarbon is itself is like new kind of research, but those have also given lots of importance to the organic solar cells to keep it live over almost a decade. So you can say that 1995 the PCBM got introduced, and the PCBM stayed in till 2010, and where the efficiency gone up to 10.1. And then we had a new discovery which came in 2015. We people learned that we have to go beyond fluorines, and they introduced some non-fluorine. So non-fluorine can be many different chemical structures, which we'll see, was introduced, and 2015 to 2020, 11% became more than 19%. So there's a paradigm shift was required. People got stuck for the 10 years with those carbon balls, fluorines, and that could make an improvement, but then 10% remained 10% for the 5 years, almost for the 5 years. 2015 was the year when people learned, okay, there is something beyond fluorine as well. And since then till now, the things are constantly improving, and lots of momentum has come. And because of that, all these many number of industries are basically taking interest. Things are going out of the lab into the fab in these industries, and those things looks promising, because the skepticism which was there was something related to stability that I'll talk. But what we have here is a lighting, a proven $10 billion industry already. In terms of the OPVs, we have some of those prototype examples. Mobile charger, which can be just wrapped up. You can open this mobile charger. And Heliatech, which is one of the German-based company which uses the organic materials, and they have made the single junction cell by operation of the small molecules. Most interesting thing, 1 gram per meter square. This is what? Lightweight. If I want to install the organic solar cell panel, it won't take long. It can be carried in one bag, and I can go down to anybody's house and I can just open that bag, and like the way you spread the bed sheet, you can spread those OPV panels. And those are very lightweight. So they are not going to basically take away your roof or your facade of the building. So these are the examples, these are the panels, OPV panels. And there are lots of installation has already taken place, which are grid connected. There are the beyond optoelectronics, sensors, RFID tags, logic circuits. These are all organic semiconductors research byproduct, and some of them are really going to become tomorrow's IoT devices, where you have everything flexible, and those can operate at few hundreds, not now like megahertz, few tens of megahertz already is shown, and expected is like it will go into the gigahertz regime, and that's where the things. So megahertz is good enough to make RFID tags, but if you want to talk IoT kind of things, so the way the things are improving in terms of the material quality, charge transport, so they are going to go in towards the gigahertz application as well. These are some of those your Samsung and Apple Watch displays where OLEDs are being used. A common notion which has basically holded back lots of researchers. I don't want to work with organic semiconductors because they are not stable. And they are indeed stable. They have poor extrinsic stability. If things are done properly packaged, then this is the OPVI's industry, which is now changed into the Armor Solar Power, German-based company. And they have this data which is over the 4 years grid connected in Frankfurt, and the efficiencies are pretty stable. There's hardly like 8% change in the efficiency over the 4 years of time. And the key is that you need to learn how to encapsulate your devices. If you have right WVTR, water vapor transmission rate, through your encapsulant material, these materials are going to survive for longer. So there's this nice article has published by this company and one of the allied journal Energy Technology, where this all data is available. So yes, we have the things which are stable as well. What is the India's perspective? That's what I'm trying to show here. We have an opportunity here with these emerging technologies, and the top panel shows the silicon solar cells in India right now. Based on MNRE results, MNRE website results, and my own knowledge about the solar cell technologies, we are not going more than 20% even with the monocrystalline silicon. World has reached to 27.6. So where the world reached in 1985, we are there today. And on the other hand, halide perovskite, which is again going hand to hand as emerging photonic technology, photonic materials for lots of optoelectronic devices. And this slide is for the solar cells. So I'm putting NCPRE, where I have my own research laboratory to make solar cell devices. So in the terms of organic and in terms of the halide perovskite, we are not very far. It's 2020. In OPVs, we can make 13-14% solar cells right now, right away in our laboratories. And those we do understand, if we are getting hand on right choice of materials, we will go where the world is today. And in halide perovskites, the numbers are also not that far. Particularly the kind of device structure which we use is as good as what is being published by some of the elite university of the world. So if we have to go towards the Atmanirbhar Bharat, self-reliance India, then we have to take a call that we have to give the importance. I don't say that we should not be investing on the silicon. Silicon is the main material for the PV technology, proven to be 25 years stability and all. But there's an opportunity where we have to put right amount of time, money, and efforts to ensure that we can go hand to hand with the world.
Dinesh, there's a quick question.
Yes.
There is a question from student Shubhra. I don't know if you've taken this. With this much advantage of photovoltaic solar cells, can this problem be solved by just expanding more industries preparing silicon wafers in India?
Silicon wafers in India, we cannot make silicon wafers because that is like some few decades old story, when the Congress was having the government and some proposal was given to make a silicon refinery. And the silicon refinery, we have to convert sand to ignite and ignite to wafers. And those ignite to wafers things like we require few thousand crores of investment. And that is like all kind of cabinet approvals and all those kind of things goes. So I remember something of that sort of, when we said that, okay, we have lost the race with the silicon, let's go for the gallium nitride refinery. And that was discussed in the cabinet, and it's already 5 years gone. So it's not the industry which can really take a decision. It's a government. It's a basically, I did not put one more important bullet point. A huge role of the policies, government policies, makes the difference the way the energy scenario will be changing in a particular country. So I do understand that yes, that question is very valid, that and that's what I was trying to suggest, that we are going for the 100 gigawatt, and one panel requires something like 72 solar cell of 6-inch by 6-inch wafer, and we don't make any of them. So there will be huge import, and that's what is the something which which decision making people should be worrying about. But lots of decisions are being taken with the consultation of very few people, and yes, it will be nice if we have the refinery, our own refinery, but that is not going to happen. By no industry is going to put up so much money. Nobody is going to compete against China. They are going to get bankrupt. So Reliance is the one whom we are collaborating as well, and they are planning to open subsidiary industries in the energy sector. But for what? Replacement of the encapsulant EVA, because they have the confidence that they will replace the EVA, which is already being manufactured by another Indian industry. But even like we are talking about something electronic wafer, and that is going to take, I think, some time. It's big thoughts will be required. Yes.
Okay. And another question is with regards to the size of the solar cells in the lab versus what we see in the big households.
Yes.
The ones that you are stating in terms of the percentages, aren't these lab scale devices, like small devices?
Yes, so that is also a very good question, and a very basically relevant question, I should say, because when we are talking about the applied research, so when I'm putting up those arrows down, so those arrows goes hand to hand with the kind of number, with the dimension of the devices which those top class labs are making. So I don't have those basically slides here. So generally people use 0.1 centimeter square, and those are being approved by the Fraunhofer or NRAL, but we are making slightly larger than that one, and going the scalability option is more about really putting up more engineering. Yes, yeah. So there is no bottleneck.
Okay.
It's all about basically the time and money and efforts. Once we put those things, we are going to go there. So the idea is, when we are investing 100 crore rupees on the solar research, can we put something like 20-30 crore in this one, or we want to put just 1 crore into this one? So that is the problem. We are putting like few percentage.
Okay.
And that's where we are going to lose the opportunity.
Okay, thanks, Dinesh.
Yeah. So the molecular electronics has got many facets, and the things are really going very well. This is like already few $1 billion, tens of billions of dollars for industry today. So, and with all this advancement, there will be further boost once the OPVs will kick in. I think the numbers will go much higher than what is predicted. And why is that? Because the vision is it's going to be low cost. So that matters a lot. Means you can always put some money when you for the trial purpose. Okay, let's try it out. If I say that one silicon solar cell module is going to cost few thousand, 5 to 10,000 rupees, would you like to try? You'll be thinking. But if I'll say that there's a OPV panel which will be going to cost you like few hundred rupees, will you try? You'll say, okay, let's try it out. So that's the thing. Economy goes hand to hand. When the Geo came, they had a different strategy to launch the product, correct? It's not the you don't go for the postpaid, you go for the prepaid with small charging. So it's a low cost photovoltaics, and the reason is, and you don't really need big infrastructure. You don't need belt furnaces with the like a few thousands of wafers needs to be diffused, thermal oxidations and all. Those are not required. If we have the baseline in our National Center for Photovoltaic Research and Education, when we wanted to basically put up a baseline silicon solar cell facility, and at the same time, I wanted to put one organic solar cell facility. So you can imagine the kind of budget difference. It will be like, I will be not even 1%, fraction of percent. So that's what is needed. So you have the right mixture of the ink, which you can put into the some printing process, and those printing process allows you to have the very high throughput, because our targets are really not in gigawatt. The way the things are changing, we would need terawatts of power in coming few decades using our renewable energy sources. and particularly for using the solar. So the 300 gigawatt, 100 gigawatt is just 0.1 terawatt. That is not going to be sufficient to meet the needs of our day-to-day change in the lifestyle. So there is a promise of the high throughput because they are not going to be processed using those 1000 degrees Celsius or more, the 1500 degrees Celsius kind of processes. These are all low temperature processes, and with the promise of the high throughput, they can be used as a roll-to-roll processing. We are going to use the materials which are like abundant, and they are not going to impact the environment. These are the materials which are like hydrocarbons, algae, and all. These are the already like naturally grown. And the target applications, let's say that we are not making those things which are going to last for the 25 years, then there are lots of niche applications, portable powers, off-grid applications, building integrated photovoltaics. These themselves are like huge in terms of commercial market. And some of those examples are already like proven to be successful in not done by us, by Europeans. It's one of the Cambridge where I used to work. They have got a company which basically sells organic solar cell panels on the pay-as-you-go model, and those are basically lighting up lots of houses in South African countries. So they are the like reason that we have to go for this kind of low cost technology, which can be afforded by those less privileged people. We cannot say to one rural area of our country in Bihar and all, okay, go, you don't have the grid connectivity. Will you able to put this 10 lakh rupees PV installation? He is going to just give us a look. So better to look for the solutions which are affordable by those people. And printing methods, there are various kind of technologies are available: inkjet, screen, flexo, offset, gravure. So if I just say that the kind of resolution is doesn't matter, because we are going to make the high throughput devices and large area devices, but most important is the throughput. So the throughput which goes into the 50,000 to 100,000 meters per hour. And when you say that I have to get the some installations which are in the megawatts or tens of megawatt or even hundreds of megawatt, then if you'll be asking some manufacturer, even in our country like Adani or other companies, they are going to take forever. First of all, because what is the kind of baseline capacity they have, and it won't be even in megawatts. So that will be like few hundreds of kilowatts or something like that. So that will take forever. But here we have an example which are like roll-to-roll printing, and that can have much higher throughput. As I was selling, 1 gram of material can deposit 1 meter square panel. So you can imagine the throughput promise which this kind of technology can give.
So you have these ways of doing it in IIT Bombay?
No, I think these kind of technologies are right now there in the flexible center of IIT Kanpur.
Okay.
So in audience, if anybody is like really getting a chance to visit IIT Kanpur, they should be really looking into this all the gravure or flexo kind of technology which is there, and they are ready to take the projects. If you say that I'm in industry or I want to open an industry, then they are going to take care for all the cost, and they are going to provide all the infrastructure and sometimes even consumables to make use of their infrastructures to develop some kind of technology.
Okay.
So we have a normal our like simple spin coating kind of processes and all.
Spin coating, yeah.
Yes, spin coaters. We just use 1 centimeter square of those kind of, or maybe few centimeters square. That is the limit. 2 inch by 2 inch, the kind of thing which I have basically established in NCPRE. Right. To if somebody wants to make pouch cell or 2 inch by 2 inch cell, so those can be basically
that can be done in IIT.
Yeah, that can be done in IIT Bombay.
Thank you.
Yeah. So the transition which took place in the terms of how this organic semiconductors evolves over the time. So we all started with those classical PPV family. First polymer LED by the Richard Fenn was made using the PPV, which got converted into the MEH PPV with this particular chemical structure. And the P3S is one of the polyethylene is one of the very famous classical conjugated polymer, which is still like any new PhD students come into the organic semiconductor lab is going to handle this thing. But over the time, this homopolymer got converted into the copolymer, where you had a donor and acceptor sitting in the same polymer chain. And so we had the just homo to donor copolymer, and from donor to we have got to the donor acceptor donor kind of systems. And even that has changed. I will show you in the recent developments, which is even having further modifications from the going from just donor to DA to DAD to something in between as well. But this took over the like 10 to 15 years, and what has happened in the 2 decades, that will be coming in few slides. But these all polymers have when you make is basically thin film out of it. In the thin films, you are going to have the various kind of geometries. Some of them will be having the crystalline regions, some of them can be having the amorphous regions, and some of these amorphous and crystalline regions, the amount of percentage of them is going to dictate the lots of interesting observations related to these materials, being it organic, low density materials. The primary excitations, whether electrical or optical, is always going to be an exciton. And that exciton, being this kind of disorder system, is always going to be a Frankel exciton, because it will be very much localized to that particular molecules where it has been generated. There are the further charge transfer states can be generated if this material is put in contact with another type 2 heterostructures. Exciton itself will be having all kind of nature depending on the spin, whether it's going to be a singlet state or triplet states. Those are these are the things which basically suggest that it's not just you inject the charge carriers and get the light output in LED, or you shine the light and you get the electron hole pair generation. The way things happen in the silicon, you shine the light, you generate free charge carriers. In this organic solar cell, it's go through an excitonic route because of the low density. It's something like the hydrogen atom. When you basically you see the hydrogen atom, the electrons always revolve around the proton. It doesn't fly away. Because and the same thing is happen in the excitonic semiconductors or low density semiconductors. The binding energy of this electron hole pair is in the range of few hundreds of MeVs. So they cannot be basically separated by the room temperature energy, which is just 26 MeV. Whereas in the silicon as well, and even the gallium arsenic kind of semiconductor, when you shine the light, you generate electron hole pair. But the binding energy of those electron hole pair is less than the room temperature energy, and hence we are seeing the free charge carrier generation. Those are Vernier excitons. If you cool down those materials, you can so see the excitonic peaks in even those semiconductors. But at room temperatures, being the excitonic binding energy less than 10 MeVs in those systems, we generate free charge carriers. Whereas excitonic binding energy in excitonic semiconductor, molecular semiconductor, or organic semiconductors are in the range of few hundreds of MeVs. So you cannot, a single organic semiconductor cannot generate photocurrent. You need to dissociate that exciton, and for that we have to do something additional to what we do just in the case of silicon and gallium arsenide. And what we do is we basically use two different kind of semiconductor. One is called donor, another is called acceptor. Why donor and acceptor? It's just with the notion is that if you have type 2 heterostructures, you have one donor whose uh, electron affinity is higher than the other one, so you can transfer the electrons. Electron will likes to go down and hole likes to stay up. So if you are optically exciting donor or acceptor, you are going to have the charge transfer. Hole will stay on the bottom level of the donor, and electron will stay on the top level of the acceptor, and you will be having a electron hole pair which will be at the interface of this donor acceptor system. So the two materials are required for efficient charge separation. You need a kind of molecular knife to break that exciton. So you have, when you shine the light on the donor, your exciton will diffuse and reach to this interface, and there is a less energy state is available, so it will get transferred. So what is the basically energy difference between the top of the donor and the top of the acceptor? That energy offset is going to be one of the important parameter to understand what kind of voltage losses we'll have, because we shine the photon of the energy of the donor band gap, but we cannot get the electron and hole which will be coming out from the solar cell, from the ITO contact and aluminum contact, with the energy more than the work function of these electrodes. So we are going to reduce the energy offset between the LUMO or the conduction band. So these are molecular semiconductors. So we don't use picture of the conduction band, valence band. We use HOMO, LUMO, least unoccupied molecular orbital, and highest occupied molecular orbital. So we use the LUMO of the donor and the LUMO of the acceptor as close as possible to do charge transfer, and that allows us to get the minimum losses in the solar cell. That is fine. So we could separate the charges, but in order to also we have to bring them out of the device. So in order to bring them out of the device, we need to have continuous pathways. So we need to have the green connected all the way till the ITU and orange connected all the way till the aluminum. And so there's kind of interpenetrating network is required. Further, the exciton cannot diffuse more than 10 nanometer. That is mentioned by this arrow. So you have to have this semiconductor mixed in the bulk form, not in the bilayer. So the way you make the PN junction in the silicon or gallium arsenide, you just make bilayer, because exciton or charge key diffusion lengths are much larger than the width of thickness of those electrodes, those layers. But being it very poor in charge transport, we make the intermixing in the range of 10 nanometer. So the exciton can diffuse to this interface and generate the charges.
Okay.
And once the charges, yes.
Quick. There are two questions that
Yes.
that have come up on the chat box. One is by Pradeep, who is if Pradeep, you want to ask the question with an audio? The question is Pradeep.
Yes. Hello.
Yes, Pradeep, ask. Yes.
Yes,
So yes, my basic question is like, is it possible to combine that inorganic and organic photovoltaics and increase the efficiency? Like,
it's a very good question, Pradeep. And those are the efforts which are making. Yes, asking that whether I can use. So there are the two ways by which you can do. You can make the bulk heterojunctions where you use inorganic and organic mixing, where electron acceptor or the hole acceptor, either of them can be inorganic and other can be organic. So you have the important advantage of the organic and inorganic both together in the single device. Or I can have the inorganic device and organic device separately, but they both are sandwiched together. I make a tandem solar cell. So I can make use of the electronic band gap of the inorganic and electronic band gap of the organic as well. And I can stack them on each other. And then I can make a device which will be using the efficiency of both the devices. And then I will be having the much higher efficiency. And the previous case, you can have the inorganic has got better charge transport properties. So they can do the proper charge transport, and organic can do proper absorption. And that will also be a win-win situation. So those efforts were also tried. However, that organic inorganic nanocomposite did not fly that well. And then the similar concept which you are telling has come up in the form of organic inorganic halide perovskite. So in organic inorganic halide perovskite, the organic component is also very important to hold the structure, and inorganic is taking care for everything as active material, light absorption as well as charge transport. So the one which I showed you in the beginning, the opportunities with emerging technology, is something on in that direction only. It's a very good question. Yeah.
And there is one.
sir, just a small query also I ask. So in this slide, the donor LUMO and the acceptor, donor HOMO and the acceptor LUMO, what will be the gap for that efficiency also here? Like,
so the gap between the HOMO of the donor and acceptor,
the LUMO, yes,
and LUMO of the acceptor, it should be good enough to get the good decent VOC. If they become too close, then that is not used, because then you are going to lose lots of energy when the electron gets transferred, because your energy is getting absorbed by either of the material. You don't have the metrics, very good absorption strength, where you have the things. I'm sorry. Oops. Yeah. So you don't have the basically very good absorption where you can directly transfer the electron from the donor of the HOMO of the donor to the LUMO of the acceptor. But you will be always absorbing directly within the donor or within the acceptor. And then you do the charge transfer, then you are going to lose lots of energy if you have the more energy offset.
Okay, thank you.
Yeah.
Thank you, Pradeep. Shudipto, Professor Shudipto Maiti has a question. Shudipto, could you?
Hi, very interesting stuff going on you're describing. I was just looking at this picture that you have right in front of us.
Yes.
Where there is a large tortuosity. If I look at the material, the hole acceptors and the electron acceptors, and I'm sure that has a direct correlation with the performance of the device, does it?
Indeed, indeed.
Okay. So if so, are there ways by chemical or physical means by which these can be tuned in a way that you would like them to be tuned? By mechanical forces during manufacturing, or putting, I don't know, surfactant-like things or something that will make them make structures which are more, effective for this charge separation too.
Yes, that is the very, very relevant, and that is the heart of this whole OPV research, and all the efforts are basically being put up to optimize this nanomorphology to get everything optimal in terms of charge generation, then exciton dissociation, first of light absorption, and then exciton dissociation, and then charge transport. So how do we basically look at these interfaces? How does the pure phase purity of these domains? And then you don't want purely phase pure, then you don't have the charge generation. You need basically phase impure domains as well as phase pure domains for the better charge transport. So this morphology, the way I have shown, is really slightly complicated than this one. You have pure domains the way it shows, but there are the domains where you have this green and orange are intermixed, and those are the regions which are connected to this pure green and pure orange, which basically takes away the charges from those mixed domains. And the mixed domains are important for charge generation, and these pure domains are important for the charge transport, and interfaces needs to be clean, otherwise you have lots of interfacial losses. These are the chemical structures which are being used, and then chemical structure induced crystallizations and the thin film kinetics, thermodynamics of these polymer chains, those all are part of this talk, and I think that I'll be covering up in coming few slides. Please stay tuned. I think we will be talking again before I say goodbye to all of you. Yes, thank you very much. It's a very relevant question, and it's very important questions which you are asking right now. I think that will keep other audience also tuned for the incoming slides. Yes.
Dinesh, 15 minutes hai, theek hai? Thoda
Are baap re. Okay, so the idea was that optimized efficiency using this organic solar cells were kept by fixing the fluorine, that bulky ball, and that kept the field for the 15 years on the halt, and we could improve the efficiency from 1% to 10%. That's what was this simulation paper also told. According to the simulation, that is like 2006 when I was doing my PhD, and I thought, okay, 10% solar cell is the like extreme, and once the 10% will be achieved, this OPV technology will be commercialized. And the idea was you reduce the basically LUMO of the donor. On the y-axis you see LUMO of the donor and the band gap of the donor. You tune the band gap of the donor and you tune the LUMO of the donor to minimize the voltage losses at the LUMO offset, and that will basically set the thing for you. And that was done. But we had something different today, and lots of such kind of things were happening, and we also were trying out with these fluorines using our classical P3SD system. Naresh did his PhD with us, and we got something very, very shiny like silicon wafer. This is a defect-free P3SD from Anil Kumar, our own collaborator, our colleague in chemistry department, who makes ultra phase pure P3SD. It's a 6-inch big sheet of the conjugated polymer which shines like a metal, and we demonstrated that how does the basically when you make this phase pure system, then you have very good vibronic features and you get much improved performances. And that when the things get phase pure, then you see the delocalization of the levels, and that gives rise to a red shift in the electroluminescence. So there is a electroluminescence and the photocurrent response, both are plotted together here. So you have those very aligned chains, and with less of amorphous region, and other downside you have this wine color, red wine color with more amorphous regions. So, and with the dotted lines of the energy levels, so that shows that that has got more blue shifted EL. So you get slight enhancement in the VOC, but overall photocurrent is more when the things are much more aligned. So there's a role of rigid regularity, that is the charge transfer state of the defect free is lower than the charge transfer state of the rigid regular system, and defect free is the one which is shown in the hand of Anil Kumar. There was another thing which the way Sudipta was telling, adding some solvent, one can further improve the efficiency of the solar cells, because what you have is like very much amorphous nano mixed regions of the polymer chain and those bucky balls, fluorine balls. But adding a little bit of solvent additives make you phase pure and phase of the fluorines and some of those polymer chains, and that gives rise to much improved efficiencies of the organic solar cells. In terms of the field factor, on the third column, the JSC, if you look at the table, you have the field factor going from 42% to 52%, and also short circuit current density going from 8.9 to 14.7 by adding the with DIO additive. DIO is basically diodoctane. It's a low boiling point solvents. So high boiling point solvent, which basically allows the polymer chains to optimize the morphology over the time. And that was clearly seen, a clear-cut change in the Urbach energy. So there is a with DIO and without DIO. Without DIO, you have a very slanted absorption, whereas with DIO, you get very steep. And that is very clear-cut signature that things are getting much more ordered in the systems from the inorganic semiconductor knowledge. And if you look at the
Dinesh, could you use the cursor? Dinesh, could you use the cursor? We couldn't see which data you meant.
Okay. Is that okay? So this is the change in the Urbach energy with and without DIO. And then again here, this is the photo deflection spectroscopy, which we got it done from the Cambridge. And this is for the pristine films, and the photocurrent response goes beyond the absorption of the pristine films because there is a charge transfer absorption as well. And that allows us to further say that, okay, additives really helps. But adding the additives, we see a slight red shift in the with DIO is red, with slight red shift in the EL emission peak, but overall lots of gain in the field factor and the JSC. Further, in order to understand this nanomorphology and correlating with that optoelectron properties, we did deliberately lots of different percentages of the DIO, not only the optimal 3%. We went from 0% to all the way 20%, and that work was done in collaboration with Achanta Venugopal to understand all these charge transport length scales. Optical simulations were done by the Achanta's group. And we could see that when we go from 0% to 20%, we see a change in the domain size. We see a phase reversal. The what was dark become the white here. So you see the what was and the photo-induced charge generations efficiency gets changed. Here you have the fluorine aggregated. Here you have chain aggregation. So by adding this kind of solvent additives, we can indeed tune the morphology, and we can go for the optimal morphology, which is at 3%, to get the equal charge transport length scales for both the systems, which is required for the more optimal efficiency of the solar cells. So that was for the fluorine case, but when we introduce the non-fluorine, then non-fluorine basically gives an idea about now you have a single junction with double absorber. So I had this orange and the green, but the fluorine does not absorb much light. But now I'm using some of the non-fluorine acceptors, which having the electronic band gap even lower than the donor system. So I can get, I'm not limited by this Shockley limit because these all are for the single absorber. Now I have got the double absorber in the same cell. And right electronic tuning between the LUMO offsets can introduce the reduced voltage losses. And we will see that how does the charge transport properties get enhanced. And at the same time, byproduct is great thermal and photochemical stability, which makes device stable. And because the transport properties got better, then I can go for the thicker devices. Those are not typical 70, 80 nanometer. I can go for a few hundreds of nanometer. And the moment I go for a few hundreds of nanometer, then the processing over the large area becomes more better, device yield increases. And that's what is like one of the example which I'll be showing you further in the coming slides. You have the donor PTB7TH and you have a non-fluorine acceptor now, not PCBM. There's some chemical structure which will be shown in the coming slide, but you got much more coverage. It's like silicon. And this is another paper from which came just recently, like few weeks back, where the efficiency of using some of this donor acceptor kind of systems crossed almost like 19%, and fill factor is touching 80%. That is like amazing. Means it was never thought, nobody could think that the organic solar cells will go that far in terms of the field factor, charge transport, as well as the efficiency number. So, and the stability data, as I showed, are really more to do with the extrinsic. If you have right encapsulant, things are going to survive for forever. Of course, when you are making this new kind of fluorine, non-fluorine acceptors, somebody has to really worry about how does these molecules will basically pack themselves, and at the same time, how does the intermolecular packing will take place, because those two things are going to dictate lots of properties of the solar cells, as it's a morphology driven. So this is the one of the example which I was just showing, PTB7TH and IEICO4F. And this is the mixing of those high resolution magnification image of the cryo electron microscope. It was done in collaboration with Dr. Emilia Liu from Monash University. And this whole of this nanomorphology has got very fantastic, this lattice fringes. These are, and these are the like FFT, which shows very nice diffraction spots. And these all things basically suggest that this molecular non-fluorine molecules and the PTB7TH, both of them have a very good packing on the individual levels, or whether they are doing something on the intermixing size or not. That was a question which we still trying to understand, because the lattice sizes, the fringes which are being seen in the cryo-EM data is really challenging to understand, because they are the almost similar kind of constants which comes into the picture when we talk about the d spacing or the wave vector related to these q values.
So what is the lattice spacing corresponding to? It is corresponding to some sort of a crystallinity in after mixing, like
yes. So the kind of whether the 2-3 molecules lamellas are being formed using these polymer films, then how many molecules or how many chains are staying together, and then whether you have mixed one or two basically this non-fluorine acceptor into this one, or non-fluorine acceptor individually, how are they packing, and the polymer chains individually, how are they packing, and on the intermix level, how are they packing. Those all peaks can be seen in the JVAX data. These are JVAX data, and the earlier one was the cryo-EM data. So we can correlate those two things. That's what we did with the PCBM earlier paper when I was talking 0 to 20% DIO additive. So there we had the GVAX, we have AFM, we have TEM data, and we could basically correlate all of them together to explain the device physics of the organic solar cell. Same thing is when we moved from the fluorine to non-fluorine, the challenges came. There all the things were happening by the fluorine long-range ordering. But here we have the ordering because of both. And peaks associated with those ordering are more or less in the similar range. And which is basically suggests that some mixing of the crystalline solids are something which is very new thing. I haven't seen much of the literature into at least organic semiconductor community, that how to mix the two crystalline solids on the lattice level. That is like going to open up the completely new physics once the people will start taking interest into this one. We are still analyzing this data to publish, but some of those things I thought is good for this stage. So these are some of those data which we are trying to understand. There are the few peaks which we have to identify, and that requires lots of quantum chemical simulations. How do we basically assign these dimensions with these chemical structures to make a kind of unit cell? And that is not that straightforward. So that is the PTB7TH ISA4F. So when we have just fluorine, then the black data is there. Now, by adding this non-fluorine acceptor, which is low band gap acceptor, we could enhance the absorption. So there was clear-cut change in the JSC, and that could make the power conversion efficiency 8.8 to 10.5 for particular this system. For even this systems, we have the efficiency crossing 12%.
Band gap, what is the band gap for PTB7?
PTB7 is something like 800, something like 1.5. Yeah.
1.5. Okay, so you're getting VOC of half of it. So 50% you are getting.
Yeah. And then there is a new series of the fluorines, non-fluorine acceptors have come. That is called Y acceptors. Those are fused ring electron acceptor kind of systems, and those have changed the scenario because those efficiency numbers have gone 15 to like now 18-19%. And these chemical structures, the people used to have this change of the core by going from this fluorine to adding up some more nitrogen atoms, which were basically making the core electron deficient. And that overall evolution took place where lots of chemical modifications was done. And with the whole idea was that how do we basically use these chemical structures to induce the crystallizations and the packing nanomorphology being changed by stacking of these systems with the intermolecular stage. And that could make huge changes in the overall efficiency numbers, going all the way from 10% to 17-18% with this PM6 systems. And these are the same family which you have the various different kind of acceptor molecules with little bit of chemical modifications by chlorinations, by changing the alkyl chain length. So this is like all guided path. It's not like just random, today I make this molecule and let's try it out.
But,
so,
Dinesh, look at the band gaps and the values. It's almost optimized.
Yes, that's what I'm saying. So larger intermolecular dipole moment, and the so over the time, these all papers have basically studied that what has happened because of those small modifications. You don't want to change the VOC. VOC is almost optimized. So electronic level tuning is done. After electronic level tuning, what Sudipto was asking, okay, how does the morphology looks like? Alkyl chain engineering is required to have the better packing. And then adding the chlorinations. So those all have introduced some kind of twistings and the dihedral angle change. So the planarization of the chains, those could introduce lots of interesting properties, and we could see a overall improvement happening 15.7 to 17%. It is very good change, but how did it took place? We won't see much change in the VOC, but we'll see changes in the JSC and the field factor.
Okay.
And it was not just non-fluorine acceptor. There was major role of the new design of the polymer donor as well. And some of those things which you have really done very well with Satish. I should have referred your work. I'm sorry for that. So these materials, new donor systems have got now this pipe bridge, which basically stabilizes the excitons, and moreover, the charge transfer states are highly stabilized. Those are hybridized CD states because the LUMO offset has reduced. So that basically makes the charge transfer state to stay much longer than what it used to be the case in the case of the fluorine. But still, they are able to do very good charge separation because now we are not playing with the spaghetti, but we have flat noodles. Those flat noodles have very highly delocalized charge transport states, which basically eventually make the charge transfer exciton very big, and you see the charge separation. So these things were going hand to hand, and this is the molecule which has got various different forms, and the efficiency is here for the D18 molecule. You look at the mobility number. It is 10 power minus 3 centimeters square per volt per second. I showed you earlier for the P3ST and PPVs. Those are minus 6 to minus 7. So there's a 2 to 3 orders of magnitude difference in the mobility of the donor system in the SCLC mobility, in the charge. It's not FET mobility, it's charge, basically space charge mobility. So those numbers suggest that, and the field factors touching 80%, and complementary absorption coming from the acceptors. So this whole slide explains the way the modifications have taken place and the things are gone better for the OPV. And how the things are happening, a lot of things happening by doing lots of processing in the same line. You make a solution, and the solutions are in the in the solution state, you can have the pre-aggregation. When the solution is cold, then you have basically lots of crystallized aggregates. If you have not these all are like, interestingly, these are like low band gap semiconductor, molecular semiconductors. Solubility becomes very big issue in these ones. And since the solubility becomes big issue, by nature, all the pi star band gaps goes into the UVS range, not NIR range. Chemists, these are the humans who are making them do NIR range. And then once you make in the NIR range, then they don't get solubilized so easily. But then we do all kind of additional thermodynamics to make them soluble. So otherwise they stay in aggregated state. So 30 degrees Celsius data, you see room temperature has got very strong excitonic, the vibronic feature. But the moment you heat it up, you have the more amorphous chains. And you have more amorphous chains at the 110 degrees Celsius. But you have 30 degrees Celsius, which are much more aggregated. And there are very strong vibronic peaks are here. You use this knowledge, and you basically, what you do is, you have a system which you basically heat it up and then cool it down. So when you heat it up and cool it down, once you have basically made them amorphous to aggregated, which was initially aggregated, you have made them amorphous, and then disordered aggregates are being used to make the films. So during the drying process, you have all this phenomena taking place, and at the end of the day, what you get is very long range ordered fibril structures. If you don't do this cold, dry, cold, you directly use hot solution to spin cast, you don't get those fibril structures which is being shown here. This is the TM image at the 0.5 micrometer length scale, and these are the AFM images. You see these very nice polymer fibers, and that basically explains lots of things. And the packing which takes place for the Y6 system, which is one of the very important system and is being used all around the globe to make very efficient organic solar cells. The way they have basically packed themselves, that suggests that how does the charge transport is being supported by the packing of this these molecules, and the packing is happening in this particular fashion because the chemical structure was tuned in the first place. And this semiconductor basically with the PM6, that PWTT new donor, have shown the efficiency crossing like 18%, and how to go towards the 20%. That was the like paper which is 2020, but now, as I was telling, the recent 19% have been crossed, and stability is not a concern. This is lab results which are showing like 100 hours of the stability data, and that suggests that by having some kind of additive into this one. And as I was telling, like that is not the thing which we should be worrying about, because inherently if these materials are stable, then that will stay stable by right packaging.
Okay.
With this, I'll summarize. First of all, I will say that I'm still surprised to see the progress. The excitonic character is not a hindrance for photon to electron conversion, because this is the way I was taught. You are not going to get very efficient, but now we have changed the scenario. We have the results, and the efficiencies are not limited to 10%. Those are 20%, and that's what is where the inorganic solar cells are standing today. They are thermally stable. There is no problem of the fluorine aggregations, which used to be the case. And if the correctly packaged cells are there, they can stay for the years. So that notion of the organic semiconductors are going to degrade, they are not going to survive. That is again something to do with the packaging of the device. And you can understand your OLED devices are not degrading even in your pocket for the years. You throw them because they become slow. You don't throw them because the display has gone bad. And the promise of the high throughput at much lower energy payback time. People already had lots of promises from the organic solar cells. Now the efficiency, which was a setback, has been resolved, and people can use those technology which were already established to make printing those cells. That will set the path for the less energy payback technology for the photovoltaics. In terms of fundamentals, we have got the states which are electronically tuned. We are going into the hybridized states. Now the hybridized states are going to stay there forever. They are not going to basically decay down fast the way it used to happen in the fluorine case. But they are eventually get separated, and we don't have any voltage losses. Non-fluorine acceptors, additional absorption window has opened that gives the higher short circuit current densities and improved nanomorphology. This crystalline lattice fringes distributed throughout the films gives you the very good field factor and the charge transfer properties. New Y series acceptors have proven to be the process tolerant with promise to provide 15% power conversion efficiency. That is like very encouraging. Means today, if somebody wants to start doing the research in organic solar cells, if they get PM6, Y6, within a month, they should get 15% solar cell in their laboratory. Thank you very much for listening. I'll be happy to take the questions, comments, suggestions from you.
Thank you, Dinesh. Thank you very much for a very comprehensive tour of what the current technology about organic photovoltaics, where does it stand? And I think you covered a lot of aspects, a lot of ground, and I think people were patient to listen. So yes, I would request you to get your video back on, and I think I can see you once again.
Yes.
So I'll let audience ask questions. Let me go with. Are there any questions for Dinesh? Yes, Deepa. Deepa has raised her hand. Deepa, please.
Yeah, just a very quick, I mean, the cryo work is quite intriguing that you're able to see these lattice fringes.
Yes.
How does the film thickness correspond with what you're seeing in cryo to what you think is in reality?
So these film thicknesses are in the range of something like 80 to 130 nanometer. And those are basically, we did lots of processing. So I'm showing you just one image corresponding to one film. But what was the project in this one? We had this same system, which we processed in the various different conditions in terms of the spin speed, in terms of the spin duration. And we could see a visual change from going from the matte finish to glossy finish of the same system by changing the spin speed or by changing the spin duration. So that that data is there.
But the matte and glossy has more to do with the scattering and roughness. I'm talking more about the
Yes.
fringes.
Yeah, so those basically went hand to hand. So we had to use those coarse films. Matte finish did not show those kind of features. But when we had these coarse films, so the length scales, which starts from the chemical structures to the nano level and from nano to micro level. So we were looking into that process of that, how the things are changing on the nano to micro levels. And we could make out that, yes, there is like things which is happening on that length scales are really becoming a kind of seeds to grow further. And those data which we got in the cryo-EM, we went back and looked into the GVAX data, which was not done by us, by others. And we could identify those diffraction spots with the Q values to the GVAX data. And some of the new peaks which we were seeing, we were not able to see that how do we basically relate. Even the GVAX data, as I was telling, those lengths.
You see, I can understand this must be discrepancy because the GVAX data would be on a different substrate, and you need, I mean, you won't get, I don't know what thicknesses they would have used for GVAX. And that would be closer to your device structure as opposed to the cryo. I mean, this is just my interpretation of. So I was just wondering, but it's quite intriguing that finally you're looking, I mean, at least the cryo route is the best route to look at if you're using electron microscopy.
Yes.
Yes.
Don't use this cryo part. So that part is really important if you want to see your phase separation.
Yeah.
And the other thing is you don't talk about your VOC because in both your cases that you showed, yes, your efficiencies and factors are good, but your VOC is decreasing when you are putting this.
Yeah, because you have the different electronic charge transfer band gap has reduced, and pure fluorine case you have the LUMO offset which is different. So, but the overall, if you see the change in the field factor, and basically our devices are yet 12-13%, and one device we have got up to 14 plus. But overall idea is that those all molecules which I'm showing the 18%, 19% all of them are really coming from just one or two labs of the Hong Kong. And those guys are really having their own industries and companies. Chemical structures have been out in the literature. But how do we basically get hold on those molecules? I don't see any problem in PM656. We will be able to make 15-16%. I don't see any problem in that one. And overall, the field factor 70-80% is a good number, because that was not the case earlier. 50-60%, so 65% is good. Going more than that one in organic solar cell was not a really easy game. But now with this all high mobilities which are being seen, that explains lots of things. That yes, you can go for the higher yield of the devices. You can go for the really touching the efficiency, which is going to go for the silicon kind of cells, or 80% field factor. It's amazing. People have gone more than beyond 80% as well. And so yes, I think what we have got is I will check what is the number for the 14% device. But there is no doubt that it cannot be done. It can be done. You have to have hands-on on those specific systems.
Okay.
Very nice. Thanks.
Thank you, Dinesh. Thank you, Deepa. There are two questions by Monami. Monami, could you unmute yourself? I did not ask the two questions. You can ask Dinesh now. Monami, can you hear me? Okay, the two questions are put in the chat. First question is, could one then construct equally efficient avalanche photodiode APDs with materials like this? So like photodiode materials.
Yeah, so photo detectors are being made with very, very less dark current, and the photo detectors are much more sensitive than the commercially available detectors, because the organic semiconductors do not have free charge carriers. Right. They are insulated by nature. There are no free carriers in these ones. So you will be always having an NIR detector, which will be much more sensitive than any commercial NIR detector, which you or NIR. Why I'm saying NIR? I'm not even worried about the UVs detector, because the NIR detector has got more problem with the thermal charge carriers. Right. So being it even in the NIR range, organic semiconductors will be having much better performance than any other detector. And there are a lot of industries are really looking into this one. Quite some amount of work is happening in our group too on this detector applications. So yes, but what you said is avalanche concept. Yes, avalanche concept was not being explored, but normal photo detector in the PIN configuration. PIN configuration in the NIR range, there are plenty of reports, and those are very promising as compared to what you see commercially.
Okay, I will take one YouTube question by Sushil Barala. Are these new types of solar cells biodegradable? Like with the organic stuff?
Yes. So I think if the substrate is right, they are.
Yeah, because you would like to degrade. Well, they're not plastics as such, but yeah, polymers are usually difficult to be biodegradable sometimes, right? So that's
yeah.
Okay. Okay.
But at the same time, the amount is so less.
Yes.
1 gram per meter square. And what you would be using 300 micron silicon versus what you'll be using like 100 nanometer organic. So if you are going to basically put up a facet of your road of your building using an organic solar cell, you are going to create all the trash within one bucket. But if you cover up the one facet of silicon solar cell and they have degraded, I think that is one of the very big challenge which MNR is going to face. What are they going to do with those 100 gigawatt panels once they stop working?
Once they're not functional?
Yeah, once they stop working. Yes. Where are we going to have this all electronic waste? And so that is another idea which people can think of as a research topic.
Yeah. And you did not mention, I guess, the hybrid perovskites. How do they compare to these? Because hybrid perovskites are now pretty much ruling the research market. People have sort of been putting the efficiency up to 29% now, 28 to 29%. So
yeah, 29.52 is the tandem solar cell performance with the silicon, and 25.5 is single junction solar cell efficiency for the perovskite. And I tried to give a glimpse when I was talking about the opportunities with emerging technologies. So there I indeed put the one arrow for the perovskite solar cell status in India as well. In India right now, perovskite solar cells highest efficiency will be in the range of 20-22%.
You guys make it? You guys make it? Or?
We make it more than 20% in our lab. And there are the two kind of device structures, PIN and NIP. And PIN is supposed to be much more reproducible and stable as compared to NIP structure.
Okay.
And that that has got slight less efficiency, but what is like anything which is more than 15-20% with the promise of the stability without hysteresis is being considered for the real industrial use. And that's what is Oxford PV also does. They use PIN structures, not the NIP structures.
Okay. Yeah. Okay. And there is one question by Shubhra. Many different renewables are used in this energy production sector. So So what's the most important about using OPV, which will be the most beneficial for India? Shubhra, could you clarify the question? I did not understand. Could you unmute yourself? Shubhra?
Yes.
Yeah.
So I was just saying that we are using hydrogens, and we are also using batteries, and in this energy production sector we are using also solar cells. So what's the most important thing about OPV that will be beneficial for, especially for India in future? That's my question.
Okay, what is most important about OPV that it benefits the society? Okay. Okay. That's
okay. So Shiva, thank you very much for asking this question. And the first answer is, as I was telling, that the economics of this country. So if we can, if an industry opens up tomorrow here in this country with very less capital investment, which is required to develop this kind of technologies, and they can deliver something which can last even for a few years. Let's say that your mobile battery lasts for 2 to 3 years. After that, you change the battery. Your laptop batteries last for 2 to 3 years. So there are lots of niche applications where you will, right now, you know, the IIT Bombay gave one very big news that, okay, students, you are studying from the home, and if you are sitting in some zone of the India where the power cut is always there. So we give you the solutions. Make your own power by silicon panel. Now the silicon panel is so expensive. Not everybody can afford. It's very easy to say, okay, go and buy, because we are sitting in Bombay, we can say this thing. But I know what all kind of students comes in my institute. So if I can promise something which will be much cheaper, might not have that kind of 25 years of lifetime of promise. 25 years, nobody uses. I don't know any panel which is installed in India has seen the 25 years by today. So and we do not yet understand the degradation. So I will say that, okay, vision hona chahiye, vision is required. However, if I can say that what is a pocket can afford in Indian socio-economic structure, if that promise can come from the OPV technology, we have win-win situation here. I'm not going to basically import any kind of silicon wafer. I'm going to ask some my chemistry colleague, okay, can you make few 100 grams of this system, and that will take care for the lots of Anil Kumar who makes the flow synthesis. He says that he will give a few kg of the P3ST polymer, phase pure, and 1 kg will take care for 1,000 meters square installation. I can cover up 10 houses, 10-15 houses of a village. So that is the idea, that if somebody can promise the everything which is Atma Nirbhar, and with the promise of stability, which we can learn by doing the right encapsulation, the way we are right now doing our consultancy project with Reliance to test their encapsulant material based on polyolefins. So if we can show that their polyolefins can have the WBTR in the range of 10⁻³ gram per meter per day, that can be used. I can ask Anil Kumar to give me some of this donor polymer or some acceptor molecules. Chemists are doing pretty well in our country. So, but if you'll be asking that, okay, let's open a silicon refinery to take care for the non-grid connected powers of this country, then it can take another decade. I don't know, our government policies, when the moment you ask for the more than this kind of funds, then it goes into the big challenges to get approvals. But
I think Dinesh, partly the thing is related to P3HT is a homopolymer and Anil Kumar can make kgs of it. However, you have just told us that donor acceptor donor or donor acceptor polymers are the winners here. So then you have to make this. So the chemical synthesis and the scaling of the chemical itself, the material itself is expensive at this point where organic chemistry is. So I think that's another
challenges
thing.
Are there.
Yeah, that's another thing has to come up from organic synthesis side. Making of these materials and specialized materials with very high amount and low cost. So if that is taken care of, then I guess.
No, it's a very valid. So I'm saying we do not have any single industry taking interest in the OPV. I showed you the list of industries coming up in that OPV evolution. All these close to 20-30 industries are working around the globe on the OPV technology, which had all this kind of skepticism. But there are the people who believes in that one. But unfortunately, neither we have industry on the halide perovskite.
Right.
Halide perovskite के ऊपर भी कोई industry नहीं है. वो भी अपने the people are putting up billions and millions on the halide perovskite research around the globe. But we are still holding our silicon. And that is also important.
Sure. Okay. And the last two questions, Monami, I tried to get I don't know him or her, maybe it's her, to speak, but she has again maybe asked the question again. Which one is better, solar photovoltaic or solar thermal power generation?
Solar thermal.
Thermal. Okay. After all that talk on photovoltaic, you just said solar thermal. Okay. कुछ भी मत करो, गरम कर दो पानी को, है? So
turbine, you run the turbines, you can temperature can goes all the way few hundreds of degrees Celsius, right engineering, right mechanical engineering will run the turbines, and you will have the side product of the hot water to take bath. What else you want? Okay.
And Prateep is asking, is there any work that has started in India in organic solar cell market? Is there, maybe he's asking for an industry that has come up?
Yes. So Moser Bear started their operations, and before they could see the real rise of the OPV, they closed their shop. And since then, I'm not aware as a major player. People might have. I have been contacted by some of those small companies. Still, I get some. Can Professor Kabra, can we make something? Right. But I don't see that R&D kind of things. Moser Bear only did. They had all the kind of roll-to-roll printing facilities and IT experting facilities and all. And most of them, I think, has gone to now IIT Kanpur Flexible Center. Okay. Because Moser Bear closed their operations, and I think they have taken their this processing line from them. So answer is it was there, and now there is none as per my knowledge.
Prateep, is that okay? Prateep, unmute yourself.
Yes. I mean to say that if there no industry, then it will also China. There will be Europe or other can capture this OSP market, and so it will be same case as for silicon industry.
Yeah, you're right. If there is no industry support in India, then it becomes also Atmanirbhar nahi ho payega.
And from the population view also, we have to do some things. Because
yes.
Yeah, Pradeep, actually the thing is, it's not industry. Before industry has got the interest. Industry is very clear. They have very clear vision. It's we who doesn't have vision. We means the people who have the control over the money of the taxpayers. So industry will come and they say, what do you want to sell? And you say that I have a cell which is 0.1 centimeter square and that can stay for a few weeks. They say, what to do with that one? So you need to basically have the lab prototype at the scale where the industry can have the faith, trust. Okay, yes, I can take it from here till there. And that's what is the difference between what is happening in the European labs, or we are sitting in the engineering, IIT Bombay, Indian Institute of Technology. Engineers are here, and we are just talking about the science. Who will talk about the engineering then?
Okay. Okay.
That's the basic problem. So like, and for that, if we want to do engineering, then we need to have the proper infrastructures in terms of the everything goes back to the manpower and the funds. And if the policymakers can take the decision, okay, yes, we do understand that this technology can serve the country, they will come forward. Industry will come forward automatically.
Yeah.
ऐसा नहीं है industry नहीं है, industry तो है ही यहाँ पे यार.
Okay. Good. Pradeep gave you a thumbs up for that answer. He really liked the answer. So, okay. Well, I think, I guess there are no more questions. And then I would sort of request all of you to I'll first conclude the session. So thank you, Dinesh, once again for a very, very comprehensive talk. And please unmute yourself and have a clap for him, as we cannot give him a physical presence, but at least unmute yourself and give a clap. So thank you, Dinesh. That is,
I appreciate it. Thank you very much.
and I would like to state that there are a lot of people working behind the scenes for the colloquium also. Rajesh Mistry and his group, they're always switching on these talks in the lecture theater. Dinesh, you can see ALT AG66. That's the lecture theater. Normally, you would have given a talk there. We just keep it on that people who would like to sit in the lecture theater and listen on big screen, on projector.
Yeah, that's very good.
Yeah.
I get always skeptical that seeing the small screen, whether the cursor is going
yes,
things are being visible or not, my field factor numbers are visible or not.
Right. So people have a chance to go there, but we don't, because of the pandemic,
COVID,
not trusting things inside the system, which is usual. I understand. So, and I would like to also bring to notice to a few people who are right here that Professor Narayan Pradhan from ISTS Kolkata will be giving the next colloquium on very interesting chemistry of nanocrystals. So, so we will wait for him for the next session of the
I will echo the same. We have some of his molecules, some of his quantum dots. Right. Those are just awesome.
Yeah.
Solid state quantum yield crossing 80%. Right. I have never seen such quantum dots. I have got lots of samples from all around the globe to make quantum dot LEDs and all, but his samples are like just unique. Yeah. So he will be sort of showing his chemistry of how he makes these very nice quantum dots. So and thank you again for sticking by for so long. And I would request all of you to actually log off if possible, and we can have these individual sessions. I actually, Dinesh, I know you have a meeting at 6. So can you join back this meeting at 6:30? Is that possible? Yes, that should be fine.
So Deepa will be meeting you, and I'll be just, I have some few questions, so maybe I'll just finish up and leave you at 6. Is that okay?
Yeah, that's fine.
Dipin is going to, Dipin, you are here? Dipin, are you here? Maybe, okay. Okay. So, so I think Monami and Saurabh Gupta and Kalavaran Mathi are still here. That's okay.